Tech Talk Tuesday, number 164. Looks like I was almost 1 minute late, or I was 1 minute late. Walking around in the project room. Everybody tune in. Appreciate y'all signing up. Hey, Bryce. .6 bore. I want to tell you about this 4.6 bore, boys and girls. This is the high end of what we feel like we can do with a Milwaukee 8. Hey, Jerry, Charlie. So I just wanted to let y'all know that just because I'm building one of these for myself doesn't mean that these are going to be kits that are available. This is really, really hard to sell as a kit because folks don't understand about this notching required on the rear cylinder, not the front cylinder, and we need all the skirt support we can get, which I've covered in many tech talks before. Hey, Ed. Hey, Sean. But I just want, hey, Chris. Happy Tuesday. Barry, how's it going? But look, just because I'm showing you about this 4.6 bore and 4.375 stroke crank, I'm just not trying to tell everybody that's what we need. That's what we're trying to talk you into. I was going to talk a little bit about these custom base gaskets and head gaskets. This is required. I had to sign a waiver. My fingers are dirty. I've been working today. I put a shifter on the Mustang today too. Let my fingers. There we go. See where I had to sign a waiver? Sorry about my dirty fingers, y'all, but I did work. That means that they don't believe it'll work. They might believe it'll work, but it's pretty sketchy. And if it doesn't work, guess who I'm going to yell at? Me. It's not for the weak at heart. This is a 4.5 bore would be about big as I would go. 4.6 bore is me stretching the limits. Here's my head gaskets. 4.6 bore head gaskets. Also, I had to sign a waiver for those. These are 40 thou. It says coolant heads, but that's not true. It's just what they are. It's a lot of issues trying to make all this stuff seal up, and I'm willing to be the guinea pig. And I'm not saying I'm the only one's ever built a 4600. I'm just saying it's not going to be like a great kit to be selling mail order. Again, let's do a little quick coverage. Lots of big block Chevrolets and Fords and Chryslers. Hey, Jim. Hey, Chris. Wetzler Edlin. How you been, my friend? I haven't seen you in forever. 4600 is a big bore, even for a Chevrolet or Ford or Chrysler or whatever. And 600 lift is also pretty impressive. But these cylinder heads are going to be flow like a LS7. The cylinder heads have 4-over intake and 4-over exhaust valves. That will be next week in Tech Talk Tuesday, as I will have those. And you can see this is the trademark of the cylinder from Moonshine, where he has the flat to index his sleeves so that all the notching for the piston oilers and the notching for the front and rear cylinders is all got timing marks on it. I know I'm spinning around, but I just wanted you to see that. That's kind of unique. Also, this particular sleeve, it's got a really thick flange that goes down in here. It's counterbored really thick, so that you have a lot of support where the cylinder pressure is the highest. And the cylinder pressure is always the highest in the last 45 degrees, first 45 degrees of your piston and ring travel. Also, these particular cylinders are not a dead copy of everybody's cylinders. These have a larger outside dimension for the mass of the aluminum so that we're not thinly bored. They are very thick bored, and they have really high quality sleeves. We'll move over here to my board. Let me get my stool. We'll have a quick swallow of this zero weight lubricant. And I'm going to tip this over. I did a little quick drawing of a cylinder pressure chart. 90 degrees before top, 45 degrees before top. TDC, 45 after top and 90 after top. This would be typical of the power stroke. This is not accurately depicted. This is a generalized drawing so I can show you guys what it is I've been trying to explain to you. When you light the spark plug over here before TDC, the pressure starts to build, the piston is coming up, and it gets peak pressure after TDC, and you hope it's somewhere between 10 and 20 degrees after TDC so that you have the crankshaft turning and the piston going down. And then somewhere over here where it starts falling off really fast, we open the exhaust valve because the work that's being done in the cylinder is already used up because the increasing area of the piston going down. So let's go over here and walk it through one time. Just cylinder-wise now, no pistons, no valves, no heads. Let's say we're at the bottom and we're compressing the mixture coming up, coming up, coming up. When you get 30 degrees before the top on a Milwaukee 8, we light the spark plug about 30 degrees before the top, and then we squeeze it the rest of the way, and the spark plug is lighting and starting to burn this fuel. And then right here about 20 after top, 20 or 25 degrees, somewhere in this range, the pressure is so high in the cylinders that something's got to give. The head gasket, or the piston, or the gasoline, or the crankshaft, somebody's got to give. So you want this crankshaft to go to rotate when this pressure gets big in here. Boom, crankshaft rotates to make power. But also I want you to notice that when this cylinder gets halfway down, let's say this is the bottom, and this is halfway down. When this cylinder is on the power stroke and it's going down on the power stroke, about halfway down, the pressure is going down so much because the area has expanded tremendously here, and we can open the exhaust valve. And then once the exhaust valve is now wide open and the piston turns around to push the exhaust out, and right at the top of the exhaust valve, closing, right at the top where we're done with the exhaust stroke, the intake starts to open, and then we start it all over again, pulling it in and then compressing it, and then we light the spark plug and boom, we turn it into power stroke again. Y'all with me so far? All right. Now, one thing that has gotten me up on the tire a little bit lately is this cranking compression thing. If that's something that you do or your engine builder does or he wants you to pay attention to, that's good, because it's like measuring something. There's 100 things to measure. This is one thing to measure. And I'm going to show you how it affects the power of your motorcycle. And please understand, you guys, please understand, with my dirty fingernails and everything, this is 100% my opinion, not your opinion, not his opinion, not the guys that have been doing this. Because look, most of these engine guys, they've been doing it for so long, they remember when we couldn't get the motorcycles to turn over. We used to have to put compression releases, drill and tap them into the heads. We used to have to put big camshafts in to bleed off, so the starter would even turn. Back in the day, man, we used to have Harleys with 10 to 1, 11 to 1, 12 to 1, and you'd put a little torque cam in it, and that thing would go, you push the button, and it would go, and kick back, and then it would break starters, break solenoids, it would break. We would be buying all these high-dollar starters. We'd be buying ring gears and pinion gears and starter gears. And we used to change the tooth pitch and the diameters. My guys on here watching right here, my friends right there, you know, like Jim Bob, he knows if you put too much compression in, cranking compression, into a twin cam or an old shovel, there ain't no way you'd start it unless you put a compression release in it. And I even had some Harleys that were so fast and had so much power that I had 2 buttons on each head. I had a front button, a back button. On the back head, I had a front button and a back button, and I had to push all 4 of them down in order to hit the starter button. And sometimes the starter wasn't good enough. We'd put a button on the end of the solenoid to engage the solenoid manually in order to get some power to the starter without going through all the relays and the starter button. Now, y'all, listen to me. I don't know what year it started, 2008, 2010, whatever. They came out with these electric compression releases on these new Harleys, man. And this whole thing right here just went right out to lunch, because we can start one up that has 300 pounds cranking compression. We can start it up. It'll go, boom, it'll crank right up when you push the button now, because the compression release is open. Open a valve and it blows, the compression goes right out the exhaust pipe. And you can hear it if you have a 2-in-1 or 2-in-2s or true duals on the back and you push the starter button, you can hear it out the exhaust pipe going, choop, 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 coming right out the exhaust pipe. That's the compression leaking. But here's the deal. Here's a chart right here. And these are my opinions, so don't get mad at me. Don't send the police. This is an opinion, okay? And we'll back it up a little bit where we can all see it. I drew theoretical pressures versus RPM. And I'm going to tell you that horsepower is cylinder pressure. P-R-E-S-S-U-R-E. Yeah, it just don't look right. But the only thing that makes your dyno sheet go up when you floor it, the only thing that accelerates your motorcycle or your car or your Chevelle or your Camaro, the only thing that accelerates it is this cylinder pressure. And you want it, you want the most of it where you're going to operate. Or you're going to run at 2,000 or 3,000, or you're going to run at 4,000, 5,000. You got to pick out a spot. Maybe 2,000 to 5,000. That's a really nice spot. How much cylinder pressure do you want in this range? Now, please understand, you guys that live and die by these numbers right here, I just want to give you a different perspective because I don't own a compression gauge. I have not ever checked compression on cranking compression on an engine. I want to know if the rings leak, so I might use a leak down tester, but my seat of the pants, my time slip, my ET slip, and my dyno sheet tells me if I have enough cylinder pressure or not. If it has more power, let's just go here for a minute and just look at this. Let's put a stock camshaft in a 124. Just say it's a 4.250 bore, like Chevrolets, Chryslers, everybody, all those cars and Milwaukee 8s and some twin cams have a 4.250 bore. Got hot in here. You can tell it's hot when you get up on the tire like I am. Okay, I'm back. Anyway, I wanted to tell you that when you put a stock camshaft, which means it closes the intake valve at like 0. It closes the intake valve when the piston goes down the intake and turns around and goes back up. It closes the intake valve at 0 after bottom. Y'all have not ever heard of a cam like that. I'm talking about, I don't care who makes them, who the vendor is, whoever. Nobody sells a cam that opens at bottom dead center. Closes the intake valve at bottom dead center. If it did, it would make more cranking compression than anybody's. This orange one means it has cylinder pressure early. It would have peak cylinder pressure between 1,000 and 1,500 RPM. It would have peak cylinder pressure, which means it would have peak horsepower in this range. And that's because it's designed to have the most. If a guy wants the most cranking compression, he should close the intake valve way early. He should, instead of closing the intake valve like a 30-30, our famous 30-30 for the Milwaukee 8, we close the intake valve at 25 degrees after bottom. So when the piston comes down, we have a lot of air going in, and then the piston goes up. And right when the piston comes back up, we slam the intake valve shut at 25 degrees after bottom, and we have enough air in there to really squeeze it and make some big pop. But a stock cam closes 25 degrees sooner than that, so it has higher cranking compression. I had a friend yesterday put a gauge on a stock 114 over at his shop, and it made 260 pounds cranking compression, a stock 114. Now, that's fine, but guess what? The horsepower on it looks just like this orange sheet. It makes a lot of power down low, and it falls over at about 3,000 RPM. Maybe it wasn't quite that bad. Maybe it was kind of like this one, whatever color this is. It had less cranking compression, and it fell over up here at 4,000. That might be like intake valve closes at 10. But look at the difference in the cranking compression. The orange one has the most, whatever color that is. I'm colorblind. What is that color, y'all? Anyway, the next one has less. This pink one has less cranking compression, and this green one has the least amount of cranking compression. But look over here. If you're going to run at the racetrack or you want to outrun your buddies and you're going to turn it 7,000 and come back to 4,000, 7,000, come back to 4,000, you want to be over here. You don't care how much cranking compression it has over here. And I know you guys that are on the tire and all excited about this cranking compression deal, I'm going to tell you a couple things. The new bikes, the new cars, and they have tuners now where you can adjust the throttle actuation. You don't have to have it wide open at 400. You don't have to have it wide open at 1,000. You have enough cylinder pressure. This air didn't come on. There it goes. All right. All right, here's what we want to know. Where do you want peak cylinder pressure? Because remember, peak cylinder pressure is where your horsepower peaks, or your torque. Wherever you want your maximum torque, that's where your most cylinder pressure is. If you want maximum torque at 1,000, close your intake valve over here and make 250, 260 cranking compression. If you want to make peak cylinder pressure, peak torque at 2,000, close the valve a little bit later than stock, and it will make a little bit less cranking compression. If you want peak torque at 4,000 RPM, which is where I like my street Harleys, I like to make peak torque at 4,000 RPM, I would have a little less cranking compression here because I'm not trying to make the most cylinder pressure at crank speed. The starter speed is about 400 RPM, maybe 500 on a really good battery. So this is an opinion, please. Again, this is my opinion. We're going no, 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 with the starter, and the compression gauge goes poof, 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 and then it'll go up and stop after 5 or 6 pumps. And when it does, you'll see how high this goes. But remember, if it's high early, let's say everybody on this page has 11-to-1 compression. If it has 11-to-1 compression and you're closing the valve at bottom dead center, you're going to make peak power about 1,000. If you have 11-to-1 static compression ratio and you close the valve a little bit later, you're going to have peak torque at about 2,000. If you close the intake valve a little bit later and you have 11-to-1 11-to-1 static compression ratio, you're going to make peak torque a little bit higher, and so on and so on. Now, how can we make this higher or lower? One thing that you can do is add cubic inches. Cubic inches always make these go up because it's 1 horsepower per inch is minimum torque. 1 foot-pound of torque per cubic inch is minimum. If you have a 107, you should make 107 foot-pounds. If you have a 103, you should make 103 foot-pounds. If you have a 145, you should make 145 foot-pounds. If you have a 143, you should make 143 foot-pounds. But listen to me, y'all. These are generalities so we can compare numbers. Now, what if you wanted to, instead of 11-to-1 static compression ratio on all of these numbers, what if you wanted more than that? Well, all of these would go up. All of these curves would go up if you put a little bit more compression ratio on it. 10-to-1, 11-to-1, now let's put 12-to-1, let's put 13-to-1, you can put 14-to-1, and all these pressures go up a little bit. But over here, going back here, this is where the catch-22 is. If this cylinder pressure happens too soon, it blows the head off, it blows the gasket out, and you'll have to adjust it. And I want you guys to listen to me. You have to adjust the wide open throttle back to part throttle. That's why they have that drive-by-wire now. So when you floor it down low, if it's spark knocking or pinging, you can pull timing out down low, and you can also close the throttle blade a little bit. And if it stops pinging and it's got 1 degree more timing than it does when it's 1 degree less than timing in it, tuned into it less than it had when it was pinging, I'd back off another degree of timing and live with it not pinging. All right, George, we got 91 octane. We got 93 octane. How can we do all this with low octane fuel? Well, you got to run low compression ratio. And I'm not talking about cranking compression. I'm talking about the real where you drip the cylinder head. And don't read it in the book or read it on a piece of paper or read it on this card right here that says this head gasket is 3 cc's or 5 cc's or 10 cc's. You got to measure it. Like right here, it says minus 10 cc, 10 in the hole, and it's got 84 cc chamber, blah, blah, blah. If you want to know, and you're so stuck on when the intake valve closes to set your cranking compression where you want it or your cranking pressure where you want it, you should cc the chambers, the domes in the hole, negative pressure, positive pressure, and you should CC the gasket. You should CC the bore times the stroke, and you'll get cylinder CCs in volume, and you will be able to divide the total into what's left of the chamber when the piston goes to the top. And that will tell you static compression ratio. This dynamic compression ratio, where you're putting all these cam timings in, are useless as long as you don't know what the real compression ratio is. Because go look at that chart, or what do people call it, that program, or they call it the calculator. They call it the cranking compression calculator. If you go look at it, it has some stuff you have to fill in. You have to put the engine size in. You have to put the CCs of the chamber, CCs of the dome, but you can't assume that stuff because you said the camshaft. This cam won't work at this compression. This camshaft won't work at this compression. Yes, it will. If you're over here at peak torque at 4,000 RPM and it's spark knocking, you need a tuner, man. There ain't nobody spark knocking over here if they got their air-fuel ratios correct and they got their compression ratio right. Not their static, not their cranking compression, but their real running compression, because cranking PSI is at 400 RPM. Cylinder pressure is where the cylinder head flow, the camshaft timing, the static compression ratio, and the RPM work together to trap this mixture to make the most cylinder pressure, i.e. torque, at the RPM you want to run. One more thing that is not considered by this program or this calculator is, if you have a 2-valve and you put the valve at 50 thou or 100 thou off the seat and you flow it at 28 inches and it flows 100 CFM, that means you're getting about 100 CFM in every time the engine goes on the intake stroke. What if it's a 4-valve where it has 2 intake valves and at 50 or 100 lift it has 200 CFM? That means you're getting twice as much air in. So this program or this calculator doesn't include airflow. If it does, it asks you what does the head flow at 28 inches, and it never asks what it flows at intake valve closing. It never asks what the head flows at intake valve opening. It only asks what does the intake valve close at. And if you check that, that's going to be at 50 thou lift. When you look at a cam card and it says like our 3030, it says it closes at 25 degrees after bottom. That's at 50 thou lift. So on the flow bench, my 2-valve with my 2 intake valves with the really big valves flows more air at 50 thou lift than Tommy Johnson's 2-valve twin cam with a 1900 intake. It doesn't flow very much at 50. So at closing speed, at closing rate, when you're trapping the mixture, there is very little airflow going through the twin cam with the little baby valve versus the Milwaukee 8 with 2 big intake valves. It's trapping a lot more air. More's going in, more's going out, more's staying in, more's getting compressed. And that's why on a twin cam we run 240, 260, 250, 270 duration on the intake and exhaust. And with a 4-valve like a Milwaukee 8, we're way down on duration. We're running 220 duration and 240 on exhaust, or 210 duration and 230 on the exhaust, because we flow so much air and we can trap it so easily with the 4-valve versus the 2-valve. And when it's the 2-valve, that means it has 1 intake valve and 1 exhaust valve. A 4-valve has 2 intake valves and 2 exhaust valves. And I know you know that, but I just thought I would share that with you. Also, I wanted to tell you that Tech Talk 164, that's a long time. That's a lot of weeks. And I'm not done talking about this yet. I don't want to wear you out or get you like George is so upset about. I'm not upset. I just want people to understand there's more. If there is a cake or some food that has 100 ingredients in the recipe, like a really fast racing engine, it has 100 ingredients in the recipe. This is 1 ingredient. And there's 99 more that need to be talked about, considered, and explained, rather than everybody saying, this cam won't work because of this, or this cam won't work because of that. Or people tell me all the time, said, my builder says that 3030 won't work because I have 11.2 to 1. And he said, I need 10.7 to 1 to use your camshaft. I'm going to tell you what, y'all, that is wrong. That's not just my opinion. I know better because I have put every kind of cam and every kind of engine. And if you have a tuner, a guy that can move the timing, move the fuel, move the throttle around, torque management, you can control all this pinging and stuff. But I'm going to tell you what, the guy that has the least amount of cylinder pressure has got the slowest motorcycle and the slowest car. If that was not true, superchargers and turbochargers would not sell, because every one of those goes way up here with a turbo and a supercharger, and it's not because of this cranking compression. It's because of the cylinder pressure is more when you pack more in there, therefore the torque curve goes higher. I'm going to have to go back and look at these comments. I'm going to have to go back and talk about all these different things, but I wanted to tell you all that, I am very thankful for you guys tuning this. Please understand these are my opinions, not the gospel of the truth on how this works, but I know the people that believe in this speed and getting this pressure that they can measure on a gauge are just as convinced that they are right as I am that it doesn't matter, because we've won a lot of races, built a lot of motorcycles, and built a lot of engines, and won a ton, and I've never checked this before in my career. I just know I want the most of this against anybody I'm running against, or for me to have fun on my motorcycle and my car. I want for this curve to be in the RPM range that I want it, and I can control that somewhat with the cam timing. And this cranking compression number is a result of some of these changes that are made. They're not the cause. This is the result. May God bless y'all. Have fun. I look forward to showing you the cylinder heads and talking more about the airflow on this big old giant 4600 Milwaukee 8 with 2 intake valves that are really big, and we had to get these big pockets put in there so we could get the +4s in there and the +4s on the exhaust. And I expect it to make 200 horsepower, and I expect it to spark knock if I don't tune it right, because it's got a lot. I might hire somebody to tell me what the cranking compression ratio is, but it's going to be a lot, because this right here, I should be 14 or 15 to 1 on static compression ratio, and I'm going to close the intake valve when it has the where I want it to have the power I want it, not to get the cranking compression I don't want. Say that back to me. Not to get the cranking compression I don't want. May God bless y'all. Good night.